Well, as you can see, this is the place where the future happens with the people of Westinghouse. This is about what we call the microreactor, where you can basically bring power to the site. Imagine needing electricity so badly that the fuel itself has to fly in by plane, ride in by barge, or crawl in by ice road. In many corners of the world, power is not just expensive, it is fragile. That is why a new kind of portable nuclear reactor is drawing attention. Westinghouse calls it the eVinci microreactor, a factory-built unit meant to arrive like a container and run like a battery. Supporters say it could replace diesel, steady a microgrid, and cut emissions fast. Critics say the costs and waste could bite back. The first real test is near. Power at the edge. Remote power is a strange world. A town or mine can be surrounded by wind, sun, and water, yet still run on diesel because the grid ends hundreds of kilometers away. Every liter has to be shipped, stored, and burned. When storms hit, deliveries stop. When prices spike, budgets break. Studies of remote Alaskan systems show diesel electricity can cost from about 50 cents to more than $1 per kilowatt hour. And that is before counting the noise, fumes, and maintenance hours. Those numbers explain why a compact always-on power source keeps coming back into the conversation. A microreactor would not need daily fuel runs. It would not depend on calm seas or clear skies. It would sit beside a small microgrid and act like a steady heartbeat, giving power and heat in one package. That matters for remote homes, but it also matters for data centers, mines, and critical sites that cannot afford long outages. It even matters after disasters when roads are broken and a temporary grid is needed fast. In that setting, the promise of a transportable reactor is simple. Replace diesel, cut local pollution, and bring stability where the grid is weakest. What makes a microreactor different? Microreactors are easy to misunderstand because they are defined less by one single design choice and more by the way they are used. First, they are meant to be built in a factory as a finished product, not assembled like a custom mega project on site. That factory approach aims to shorten schedules, cut labor, and reduce surprises. Second, they are transportable. Their output is measured in megawatt of electricity, often in the single digits up to a few tens. Many definitions place them below about 20 megawatt electric, with some stretching to 50. Either way, they're tiny compared to a gigawatt nuclear plant. They can move by truck, rail, or ship, which makes them useful in places where building a large station would be impossible. Third, they are designed for very low staffing. The goal is self-regulation and passive safety, where the physics of the reactor helps, slowed down when temperatures rise, and where heat can still leave the core without active pumps. Put those three traits together, and a new use case appears. Instead of feeding a national grid, a microreactor feeds a microgrid, a mine, a campus, a port, or a remote community. It is not competing head-on with the biggest reactors. It is competing with diesel generators and long transmission lines. Inside the eVinci swap like a battery idea, Westinghouse's entry in this space is called the eVinci microreactor. The headline claim is portability with long endurance. In public materials, the unit is described as delivering up to 5 megawatt of electricity and also providing useful heat with an operating cycle of 8 or more years without refueling. The reactor is designed to sit above ground, use no cooling water, and be installed and started in less than 30 days. The company even talks about swapping it out at the end of life, like replacing a large battery, so site can keep running while the used unit is shipped away for servicing and fuel handling. The hardware follows a simple layout: a reactor core, heat pipes, and a power conversion unit. The fuel is based on TRISO particles, tiny kernels of uranium compound wrapped in multiple protective layers, including silicon carbide that act like mini containment shells. Fish in the core produces high-temperature heat. Instead of pushing water or gas through a complex loop, uses metal heat pipes filled with an alkaline metalworking fluid. Heat makes the fluid boil. Vapor rushes toward a cooler end and it releases its energy to the converter. The vapor then condenses and returns through a wick by capillary action. Because the cycle is passive and has few moving parts, It is well suited to a small reactor. The power block is typically described as an open-air Brayon system, turning that heat into electricity with high reliability. Now, first, like always, be sure to hit the like button down below. It helps us out tremendously with the reach of this video. Thank you. From promises to proof at the dome testbed, a concept only becomes real when it meets regulators, engineers, and time. In late 2024, the U.S. Department of Energy announced that Westinghouse had completed a front-end engineering and experiment design package for an eVinci prototype experiment. That work, often shortened to FEED, is not a mere drawing set. It lays out schedules, budgets, test plans, and a preliminary safety case that the next steps depend on. The experiment is aimed at the demonstration of microreactor experiments music. It's a facility known as DOME at Idaho National Laboratory. DOME is being built by repurposing the old experimental breeder, Reactor 2 containment music structure, and is intended to host fueled tests of microreactors up to about 20 megawatt thermal. In mid-2025, the DOE made conditional selections for Westinghouse and another developer, Radiant, to pursue the first DOME campaigns, with the first fueled experiment targeted as early as spring 2026. Meanwhile, interest is not limited to the United States. In Canada, the province of Saskatchewan announced roughly 80 million euros Canadians, reported as about 53 million to the Saskatchewan Research Council to support a first microreactor project, with AI named as the design being pursued in public timelines, pointing to operation around 2029. These steps do not guarantee success, but they do show that the idea has moved beyond slide decks and into real facilities, real permits, and real deadlines. The big hurdles, cost, fuel, and the 55,000 tons claim. Even with a clever design, microreactors carry heavy questions. The first is economics. The best case numbers often assume mass production and many units built because factories get cheaper with repetition. A U.S. national lab techno-economic assessment has suggested that an nth-thickened microreactor could reach levelized electricity costs around $140 per megawatt hour under optimistic assumptions. But it also notes that early units face uncertainty in capital operations, music, and fuel logistics. In other words, the price could be higher at first. That sounds painful when compared to low-cost renewables on a strong grid, but the comparison changes in diesel regions. If a village is paying 50 cents to over $1 per kilowatt-hour for diesel power, then even a high microreactor cost can look competitive, especially when it cuts delivery risk and local emissions. The second question is fuel and waste. TRISO fuel is famous for toughness, yet it is complex to model, and the surrounding graphite can drive up the volume of spent fuel per unit of energy. Research and lab write-ups note that TRISO-based systems can create much larger spent fuel volumes than conventional music light water reactors, which complicates storage and disposal planning. Finally, there is the catching climate figure. Westinghouse materials say a single ion can avoid up to 55,000 tons of CO2 per year. But that number depends on what it replaces. If it displaces round-clock diesel generation, the savings can be huge. If it replaces a cleaner grid mix, the savings shrink. So, the real value of eVinci is not universal. It is targeted. The strongest case is where diesel dominates, grids are weak, and reliability is worth paying for. So when could it show up in the real world? People usually ask one question after the diagrams: when can it be bought? For microreactors, the honest answer is that the calendar depends on testings, fuel supply, and licensing all moving at the same time. DOME is important because it is designed to create hard data from a fueled experiment, not just computer models. If the first campaigns begin in 2026, the following years will be about proving steady operation, validating heat removal, and showing how the unit behaves through normal transients and off-normal events. In parallel, Westinghouse has to lock down a fuel pipeline because TRISO 4 high-assay low-enriched uranium is not yet a commodity. You can order like diesel. Then comes the regulatory path. The company has already been engaging with U.S. regulators on methods and safety cases. but a commercial deployment still needs a site, an operator, and an approved plan for security and spent fuel movement. That is why early deployments are often linked to government-backed demonstrations. Saskatchewan's publicly discussed goal of an operating microreactor around 2029 shows the pace officials consider plausible. If everything stays on track, wider rollouts would likely follow after that, once the first units have a track record and the factory line can scale. So, the market window is best described as late 2020s for first demonstrations, music, and early 2030s for broader niche adoption. It is not tomorrow, but it is also not a distant science project anymore. Portable microreactors are not a magic fix for the whole grid. They are a tool for the places the grid struggles to reach. If the eVinci can prove its heat pipes, fuel behavior, and safety case in the dome testbed, it could open a new market where diesel still rules and outages are normal. If it cannot, it will join a long list of nuclear ideas that looked perfect on paper. The next few years will answer the big questions: real cost, real reliability, and real waste plans. Until then, the debate stays alive, and the timeline to deployment asterisk. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button. Share your thoughts in the comments below. And don't forget to subscribe and turn on notifications so you'll never miss a future update. We've got a lot more exciting tech stories coming your way. Until next time, stay curious, stay inspired, and we'll see you in the next video. Goodbye.